Hi everyone. Today we're going to discuss the mole. More specifically, we're going to go over the topic of chemical quantities. So when discussing the chemical quantities of a substance, we usually use one of three ways in order to measure matter in terms of quantity. One way is by the mass of the substance. If we're ever measuring the mass of the substance, we would typically measure it using grams. Another way to measure the quantity of matter is through its volume. And for volume, we would use liters. And the third thing that we're going to use to measure the quantity of matter is typically referring to the amount of it or how many pieces there are, and for that we're going to use the mole. Now what the mole is a measure of the number of pieces or amount of each particle present within a sample. Now a representative particle would refer to the type of substance that we're working with, and depending on the substance we would just give it a different name for the type of particle that would represent it. So, for example, if we are dealing with monatomic elements, the representative particles for those are called atoms. So an atom would refer to the particle if we're just dealing with a singular particle of an element, so just one atom of an element. If we're dealing with a charged particle, then of course we refer to those as ions. Now suppose we have two elements bonded together forming a compound. If that compound is ionic, then the representative particle to refer to in a compound is called a formula unit. Now, if that compound happens to be molecular or having a covalent bond into it, we will refer to the type of particle as a molecule. Lastly, we have a special class of diatomic elements. Now, those diatomic elements are those that exist as a pairing in nature. And just as a refresher, our diatomic elements would be bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All of these elements exist as a pairing in nature, and so they're referred to as diatomic elements or two-atom elements. Now, because these two atoms are sharing a covalent bond between them, diatomic elements are also referred to as molecules. But these 7 elements are the diatomic elements. Now, these are the different types of particles that can represent whatever a substance is, depending on what the substance is. A mole refers to how many of these particles are present in a sample. More specifically, if you're dealing with 1 mole of a substance, we are usually referencing having 6.02 times 10 to the 23 particles of whatever that substance is. We can think of the mole similar to how a dozen represents 12. A mole would represent 6.02 times 10 to the 23. And this could be of anything, but because it's such a large number, we typically only really ever use it when we're discussing particles because of how small they are. Now, when we reference mass, it is important to know exactly which type of mass we're working with, because that's going to affect the unit that we deal with. So, for example, we have different types of mass. The atomic mass refers to the mass of a singular atom, and we would use that with the unit of AMU, or the atomic mass unit. If we're dealing with the mass of a compound, we will usually refer to that as a formula mass or a molecular mass, something to indicate that now we're dealing with a compound, so multiple atoms together, and we still reference that in AMU. Now suppose you have 1 mole or 6.02 times 10 to the 23 particles of something. The mass of that sample would be referred to as molar mass, and that is measured in grams. So for practical use, molar mass gives us a way to work with the mass of substances in grams rather than AMU, so that it's more appropriate for the scale of a lab. But molar mass very specifically refers to the mass of 1 mole of a substance. So if we have 6.02 times 10 to the 23 particles of whatever substance that is, the mass would be referenced to that quantity. So we can see here that the mole can be related to 2 things. We can relate the mole to particles and represent the actual quantity of something, or we can represent the mole to mass. Depending on how we want to relate the mole, we just use a separate conversion factor. When relating the mole to particles, we typically work with the fact that 1 mole is equal to 6.02 times 10 to the 23 of any type of particle that we're dealing with. Now, when we're trying to relate the mole to mass, we would usually work with molar mass because that refers to the amount of grams in 1 mole of something. So let's see some examples on how to work with the mole and how to do some conversions with it. So in our first problem here, we want to know what is the mass of 2.50 moles of oxygen gas. So we are given 2.50 moles, and this is of oxygen gas. So it's important here to note that we are dealing with standard state or natural oxygen. And if we refer back, oxygen is one of our diatomic elements. So that means when we're referring to oxygen, we are not referring to it as O, but rather as O2. And that's a really important distinction to make here, since it does change the type of particle we're referring to, but also what the molar mass is that we're dealing with here. So we have 2.50 moles of oxygen gas, and we're looking to find the mass of this. So if we set up our dimensional analysis, we are converting our moles into grams, our mass. So we want our grams, and so we'll put that in the numerator. We already have our moles, and now it's a matter of just filling in what the conversion is. Since we're dealing with grams per moles, that is molar mass. And so molar mass refers to the grams in 1 mole. These are values that can be taken straight from the periodic table. Since oxygen has a molar mass of 16 grams per mole, O2 would have a molar mass of 32 grams per mole. So our conversion factor would be 32 grams for every 1 mole. This right here represents the molar mass of our substance, which here is oxygen. So then our conversion becomes 2.50 moles of O2 times 32 grams for 1 mole, and that gives us 80.0 grams of oxygen gas. And it's important to note that we are keeping track of our sig figs, so we do want to represent our answer as 80.0 grams. But there you have it. This is how we convert from moles to mass using the molar mass. In our second example, we want to know how many moles are contained in 4.95 kilograms of potassium cyanide. So here we are given 4.95 kilograms. Now we're looking for moles, and moles to mass would involve grams. So currently we can't really use our measurement of kilograms. We would first have to convert this into grams. So we're going to take our kilograms, set up our conversion. We want grams, we have kilograms. There are 1,000 grams in 1 kilogram, and so we have 4,950 grams of potassium cyanide, which is KCN. So we're going to start off with our 4,950 grams of potassium cyanide, and we want to convert that into moles. So we want moles at this stage. We have grams, and once again, we're seeing our conversion factor requires grams and moles, which is our hint to work with molar mass. So we will need to find the molar mass of KCN. So we break down the components of potassium cyanide, and we just check the periodic tables for their masses. Potassium has a molar mass of 39.1 grams per mole. Carbon has a molar mass of 12.01 grams per mole. And nitrogen has a molar mass of 14.01 grams per mole. We add all this together, and we get that the molar mass of KCN is 65.12 grams per mole. So then if we head back to our conversion, within 1 mole potassium cyanide, that would be 65.12 grams. So then we take 4,950 grams of potassium cyanide times 1 over 65.12, and that gives us 76.0 moles of potassium cyanide. So in the first case, we are essentially multiplying by molar mass to convert from moles to mass. And in the second case, we are dividing by molar mass to go from mass to moles. Either way, setting up our units and following the steps of dimensional analysis helps us to get the appropriate conversion, but this required us to know that we have to use molar mass. This is the way to relate together the mass and the mole. Now for that final measurement that we talked about earlier, volume. When we're discussing volume, when it refers to moles, many times we're referring to things at STP. STP stands for standard temperature and pressure, and it's a set of conditions in which this gas is present at. The conditions are a temperature of 0 Celsius or 273 Kelvin and a pressure of 1 atmosphere. Avogadro's law states that if we have equal volumes of gases, if they have the same temperature and the same pressure, then they will have the same number of particles, which also means they contain the same number of moles. And when we are at STP, 1 mole of any gas will occupy a volume of 22.4 liters. We refer to this as molar volume because it gives us a relationship between volume per mole of a gas, and again, this applies to any gas. When we're referring to molar mass, it's specific to whatever the substance is. Molar volume, however, is uniform between all gases so long as you are at STP. And at STP, 1 mole of any gas occupies a volume of 22.4 liters. So we can use that now as a way to convert between moles and liters. So if we put all this together, we can create what's called the mole roadmap. The mole roadmap shows the link or the conversion with the mole between these 3 different factors. So between volume, particles, and mass. Each one is a matter of just what conversion factor is needed and what direction are we going in. So if we want to go from moles to particles, we've seen that 1 mole of anything is 6.02 times 10 to the 23 particles. So going from moles to particles require us to divide by this number. And if we're heading from particles to moles, we are just dividing by it instead. Moles to mass, if we are going that direction, then we have to multiply by molar mass. And if we're going from mass to moles, like we saw before, we are dividing by this. Lastly, if we want to go between moles and volumes, then we have to multiply by 22.4 liters. But if we're going to go from volume to moles, then we divide by 22.4. So this mole roadmap shows us the different ways that we can convert these different measurements with the mole and exactly which conversion factor needs to be used. So let's take a look at a few mixed mole conversions and to see a jumble of different things that we can convert with the moles and with each other. So first, we want to find out what volume is occupied by 4 moles of helium gas at STP. So we have 4 moles of helium, and it's always good to get in the habit of labeling our substances so that we can keep track of exactly what our unit is representing. So in this case, we have 4 moles of helium, and we're looking for its volume at STP. And it is very important that we specify here that we are at STP. Because of the fact that we are at STP, we can use our molar volume. So we're going from moles, and we want to hit liters, which is volume. We already have moles. Now at STP, 1 mole of any gas occupies 22.4 liters of space. So 4 moles of helium would occupy a volume of 89.6 liters. In our next example, what is the mass of 36.7 liters of argon gas at STP? So here we're looking for mass, and we're given a volume instead. So if we just refer back to our mole map, you'll see that there's no direct link between mass and volume. So we can't just one-step our way from mass and volume, but instead we can see that they are linked through the mole. So this is going to be a two-step problem. We would have to convert our volume into moles and then our moles into mass. So we have 36.7 liters of argon, and we must first convert it into moles. So we want moles right now. We have liters. 1 mole of any gas is 22.4 liters of volume, and that gives us 1.64 moles of argon gas. We then take that and multiply, looking for mass, having moles already, and now that we're dealing with grams and moles, we want to go back to our molar mass. Now here, we would just look at the periodic table for the molar mass of argon. There are 39.95 grams for every 1 mole, and we find that this is equivalent to 65.5 grams of argon. So 36.7 liters of argon would have a mass of 65.5 grams. So now in the last question, we're asked how many formula units of magnesium nitrate are present in a 12.4 gram sample. And then the second part, how many nitrate ions are present. So first, let's go back and take a look at our mole roadmap. We'll see that we have mass here, and we are asked for particles because formula units falls into the category of particles. Now, the way to go from mass to particles involves having to pass through the mole. So that's going to be our first step. We're going to want to take 12.4 grams and convert this into moles to then convert it into particles. So we have 12.4 grams of magnesium nitrate, whose formula is MgNO3 2. We need to convert this into moles, and we are given a mass already, and so we are going to need the molar mass of magnesium nitrate. So if we work through our molar mass calculations, we'll see the magnesium nitrate has a molar mass of 148.33 grams per mole. This step will get us moles of magnesium nitrate. We can then add on another step, converting it into formula units or particles. So we now have moles, and in 1 mole, there are 6.02 times 10 to the 23 particles. This, in the end, gives us 5.03 times 10 to the 22 formula units of magnesium nitrate, MgNO3 2. Now in the second part of this problem, we are asked to find how many nitrate ions are present. Now this is where the labeling becomes really important, because we are again asked for particles, but now it's not the same particles. These are now ions we're looking for, not the entire formula unit. If we look at the chemical formula of magnesium nitrate, we'll see the subscript of 2 here by the nitrate. This tells us that there are 2 ions of nitrate for every 1 formula unit of magnesium nitrate. So there are twice as many nitrate ions as there are formula units of the whole magnesium nitrate. So if we have 5.03 times 10 to the 22 formula units of magnesium nitrate, then we should have twice as many nitrate ions. And if we set that up, we have our 5.03 times 10 to the 22 formula units of magnesium nitrate times a 2 nitrate to 1 magnesium nitrate ratio. We get 1.01 times 10 to the 23 nitrate ions. So the labeling here of formula units, magnesium nitrate, and just the straight up nitrate ions makes a difference in the actual numerical value, since we have twice the number of nitrate ions than we do of the entire formula unit. So this is how we convert with moles and a variety of different units. We just have to reference our mole map, know which conversion factors apply, and know essentially what direction we're going in to determine whether we are multiplying or dividing by these values.